Welcome to another EMWorks webinar session. Before we begin, a quick note on questions. There will be a Q&A session at the end of the webinar. You're welcome to type your questions in the live chat box at any time during the presentation, and we'll address them during the Q&A section. In this session, we're going to look at a problem that many engineers encounter sooner or later when working with DC solenoids, which is the gap between what we expect during design and what we actually measure on the prototype. The title of this webinar is Why DC Solenoids Underperform in Practice, Coil Design and Voltage-Driven Thermal Effects, and the focus is very specific. We're not talking about manufacturing defects or poor materials. We're talking about design assumptions, particularly around coil design, voltage-driven operation, and thermal effects that quietly shape performance in ways that are often underestimated. The goal today is not to criticize traditional design approaches, but to explain why they break down in practice and how a more realistic modeling mindset helps avoid late-stage surprises. Most DC solenoids are still designed using a set of assumptions that seem reasonable at first glance. We often assume the solenoid behaves as if it were current driven, with a fixed current flowing through the coil. Under that assumption, force becomes proportional to the product of current and turns, the familiar NI relationship, and temperature is treated as a secondary effect, something to check after the electromagnetic design is done. The issue is that this mental model does not reflect how most solenoids are actually powered in real applications. In practice, they are voltage driven, not current driven. And once you accept that, the electrical and thermal behavioral become inseparable. This is why this topic matters. If the assumptions are wrong from the start, the prototype will reveal it later, often in a costly and frustrating way. To examine this properly, we modeled a voltage-driven DC solenoid rather than an idealized current-driven one. The geometry was kept identical across all cases, and the supply voltage was the same in every simulation. What was deliberately changed was the coil design, specifically the wire gauge and the corresponding number of turns that fit into the same available space. Copper resistance was treated as temperature dependent rather than constant, meaning that as the coil heats up, its resistance increases and directly affects the current. This setup isolates the real design trade-offs engineers face when choosing wire gauge and turn count under a fixed voltage supply. The results clearly show that changing the wire gauge affects many parameters simultaneously. Force is only one of them. A thicker wire reduces resistance and allows higher current, which increases force, but it also increases copper losses significantly. Thinner wire allows more turns, but resistance rises and current drops. Inductance, flux linkage, NI, and copper loss are all linked. Under voltage drive, it's not possible to optimize one parameter in isolation. The key takeaway here is that coil design under voltage drive is inherently a coupled electric and thermal problem, not just a magnetic one. When comparing plunge force across the three coil designs, the geometry and voltage are identical, and only the wire gauge changes. As expected, thicker wire produces higher force. AWG delivers the highest force, followed by AWG23 and then AWG30. At first glance, this might suggest that thicker wire is always a better choice. However, that conclusion only holds if the thermal cost is ignored. The electromagnetic benefit is clear, but it represents only part of the overall behavior. Copper loss rises rapidly as wire thickness increases. The same design choice that boosts force also introduced a strong thermal penalty. This highlights a critical point. Force increase is not free. A higher current under voltage drive leads directly to higher I squared R losses and increased heat generation inside the coil. If this heat is not accounted for during the design, it will later appear as rising temperature, increasing resistance, and declining performance. Even with careful coil optimization, certain limits cannot be avoided. As long as the solenoid is voltage driven, the temperature rise and resistance increase are inevitable. Coil optimization can shift where the compromise sits between force, efficiency, and heating, but it cannot remove the coupling between them. This is why optimization alone cannot resolve underperformance if thermal behavior is ignored. Under voltage drive, resistance becomes a controlling factor. As temperature rises, copper resistance increases. Because current is equal to voltage divided by resistance, any resistance increase directly reduces current. Since force depends on current, force inevitably decays as temperature rises. This behavior is not an edge case, it represents normal operation for voltage-driven DC solenoids. Steady state temperature is not a minor correction applied after electromagnetic design. It is a dominant effect that controls resistance, current, and ultimately force. Once thermal equilibrium is reached, the electrical operating point is fundamentally different from the cold condition assumed during early stage calculations. Treating temperature rise as secondary leads directly to unrealistic performance expectations. Current does not remain constant over time. The initial cold current is often used during the design, but it exists only briefly. It does not represent normal operation. As the coil heats up, resistance increases and current decays until it reaches a steady state value. Designing for cold current means designing for a condition that never lasts. The same behavior appears when force is examined over time. The difference between cold force and steady state force is substantial, dropping from 10.6 newtons to roughly 6.2 newtons, corresponding to a reduction of approximately 41%. This directly explains why prototypes often underperform once they warm up. This discrepancy is not caused by unexpected physics, but by unrealistic assumptions made during design. In practice, this pattern appears repeatedly. Solenoids are designed using cold current assumptions, but tested at steady state. The measured force falls between expectations and the prototype is labeled as underperforming. In reality, the device is behaving exactly as predicted under voltage-driven thermocoupled conditions. The disappointment comes from the mismatch between the design model and real operating conditions. When examining what truly limits DC solenoid performance, the dominant factors become clear. Voltage drive sets the operating framework, thermal rise follows, resistance increases, and current decreases as a result. Magnetic saturation can occur, but in many practical cases, it plays a secondary role compared to electrical and thermal constraints. The primary limitations are inherent to how the device is powered and dissipates heat. Thermal effects must be included from the beginning of coil design. Voltage drive fundamentally alters force predictions compared to current-driven assumptions. Force should always be evaluated at operating temperature rather than at cold startup conditions. Adopting this approach significantly reduces the risk of late-stage redesign. DC solenoids are inherently multi-physics devices. Electrical, thermal, and magnetic effects are tightly coupled and cannot be treated independently without sacrificing accuracy. Simulation enables these interactions to be captured early, allowing for realistic design decisions. Ignoring the coupling does not simplify the problem. It merely shifts failure to the prototype stage, where changes are more costly. To close, it's important to briefly clarify how the results shown here were obtained. All results presented here are based on coupled electromagnetic and thermal simulations. These simulations were performed using EMWorks EMAG, which solves electrical, thermal, and magnetic effects together within a consistent framework. This level of coupling is essential for analyzing voltage-driven devices such as DC solenoids. Thank you for joining this webinar and for spending time with us today. If you'd like to go deeper into the topic of DC solenoids, you can find additional technical details and practical considerations in our application notes, which cover modeling and design aspects in more depth. We'll now move to the Q&A section. If you've posted questions in the live chat, we'll go through them now. And if you still have questions, feel free to type them in the chat and we'll address as many as we can. Thank you.
Okay, thank you. Thank you all. Um, so, still, if you have any questions, we're open to questions. But the bottom line, the message that we are trying to tell you as a designer, solenoid designer, is you have to pay attention to the wire gauge of your coil. It's a wire gauge makes a difference, and the thermal also makes a difference. You cannot model a solenoid without taking into consideration the heating effect. Okay, the heating effect also going to depend on the wire gauge. So, uh, as thicker wire give you larger force, but at the price that eventually you have to pay, because when the resistance increases, the current decreases, and the force is going to decrease as well. So you have to manage all of these issues. They're not. Uh, you cannot ignore any of these issues. So the wire gauge, the temperature dependence, uh, all have to be taken into consideration. And you cannot actually, even though it's DC, you can't just say, okay, it's a current driven. I know the current. No, it's not like that. You have to model it as a voltage driven, because the current is going to depend uh, on the resistance, and the current is going to change as the resistance changes, as temperature changes, resistance is going to change, and current is going to change. So you cannot model your solenoid as a constant current. It has to be as a DC voltage in case a DC coil, DC, it's a DC solenoid. Oh, that's basically, I hope the message is clear. If you have any uh, other questions, you can email us or you can text us. We will be happy to answer any of your questions. Thank you. Thank you all for your time. Bye now.